everyone. It's my pleasure to welcome you to our morning session. And we're starting off today with Torsten Endlin, who's going to tell us about Bayesian basics.
Okay. Good mornings and greetings from Germany. I'm Torsten Endlin. I'm at the Max Planck Institute for Astrophysics, and I'm also at the newly founded German Center for Astrophysics in Görlitz in East Germany. Today, I will give you an introduction to Bayesian basics. Okay, let's start very basic. So let's look at star lovers. So imagine the following situation. You are at a party, and there you meet one of the most attractive person of the gender of your desire, and you start to talk to that person. And it turns out that this person is a star lover, and your attention goes up. This might be an astronomer. Fantastic. And so while you are thinking how this might evolve and how you might know this person closer, maybe get together, engage, found a family, you realize, maybe it's also could be an astrologer. So you might want to be careful, right? Who wants to marry an astrologer if you can marry an astronomer? While you talk to that person, you find out that this person also loves math. That's great. Because according to your experience, typically astronomers like math, where most of astrologers are not so much mathematicians. So, and according to what you have observed, you think that 90% of the astronomers actually love math, and only 10% of astronomers hate math. Where with astrologers, it is the other way around. Okay, most astrologers hate math and only 10% love math. Okay, so the signal, the quantity you want to know, is a person an astronomer or an astrologer? That is S. The data you got in order to be informed about that important question is the fact that this person loves math. So what I've given you is the so-called likelihood, the probability of the data given the signal, and from which we want to draw our conclusion. So the data, the observed data says this is a math-loving person. Is it an astronomer or is it an astrologer? So the big question of your heart is, who is this? Is it an astronomer or an astrologer? So now I want to ask the audience, who of you thinks it is an astronomer? Please raise your hands now. And I would ask someone from the organizers to count roughly how many people are raising their arms. Can I get this number as soon it is?
Between 200 and 300, probably.
Between 200 and 300. Excellent. Who thinks this person is an astrologer? Please raise your hand now.
Between about 20 and 30.
Okay, excellent. And who thinks it's 50-50? The chances that this is an astronomer is as large as this is an astrologer.
Just max.
Pardon?
We got 2.
2. Okay. Let's investigate the situation. It is an absolutely essential situation, right? Your next move might depend on it. And remember, the future of your kids might depend on what you do next. And other people are also interested in this person. Okay. What we have looked at is the likelihood, the probability that given this person is an astronomer, the person loves math, and the probability that given the person is an astrologer, the person loves math. What we, however, want to know is the other opposite direction. What is the probability that this is an astronomer or an astrologer? And in order to construct this we have to fold in how many astronomers and astrologers do exist on this planet. And if you ask random people whether they are more familiar with astronomy and astrology on the street, you find out that, well, many believe in astrology, but only a few know the basics of astronomy. So let's say 10% are astronomers and 90% are astrologers. Okay, so if we fold this prior information in and calculate the joint probability of a person being astronomer or astrologer and loving or hating mass, then we get the following number. And in the category of people who love mass, only 9% of the, only 9% love mass and astronomy, and only 9 of all people love mass and are astrologers. So if we normalize now to all the people who love mathematics, which are 18%, the probability to have observed the data we observed, if we normalize to this number, then we get the desired number, the probability for the signal, whether the person is astronomer or astrologer, given the data. And in this particular case, it turns out to be 50-50. So congratulations, 2 of you were right. Well, so what should you do with this information? Did you learn something? You seem to be now a bit, well, your chances are only 50-50. However, if you look at the initial chances that a random person is more an astronomer than an astrologer, these were 10-90. So actually, the update you got by the information that this person loves mass has improved the situation, and maybe you should continue and investigate whether this is a person you want to spend more time with. What I've done with you is a small psychological experiment. Well, first I've used Bayes' theorem in order to do this update, and then I've framed this in a psychological experiment. This experiment was invented by Daniel Kahneman, a Nobel Prize winner, and actually goes very much along the lines of what I've done with you. And you might feel that I have tricked you into the wrong answer. Well, if I did this experiment with myself, I did exactly the same mistake. Why do we do these mistakes? In his book, Thinking Fast, Thinking Slow, Daniel explains that when our brain is acting under time pressure, it only looks at the likelihood only. It only looks whether the data you get, the information you get, fits to the signal on a likelihood level. We do not consider so much how probable the condition we are looking at actually is. This allows us to make fast decisions and to react maybe to a danger. However, it is not the best in order to do concrete or precise logic. If we have more time, then our brain switches to the slow thinking, and we not only consider the likelihood, but we also fold in the prior information we have about the conditions we are looking at. In this case, could this person be an astronomer or an astrologer, this star-loving person? And of course, I used all psychological tricks I'm able to use in order to get you into this fast thinking mode, so that you experience the problem. Nevertheless, so for scientific problems, I would recommend going to the slow thinking mode, where one takes prior and likelihood both into account. So ideally, we would love to do our scientific reasoning following logic, Aristotelian or Boolean logic. That is, however, only concerns with values of true or false. So if in his book, The Mathematical Analysis of Logic, George Boole explained the formalism, how to calculate with truth or false values for statements. And say if A is a statement, the combination of A with an or and A, so if you say A or A, this is as much true or false as a statement A alone. Also, the combination with an and, A and N, the logical product, here written as a product of these two statements, has the same truth value than A. And the algebra of Boolean logic is probably known by each of you. And that would be the thing we ideally would like to use in order to do deductions. But even in the small example which I presented you at the beginning, this was not possible because there was uncertainty involved. And so another smart person, namely Maxwell, said the actual science of logic is conversant at present only with things either certain, impossible, or entirely doubtful, none of which, fortunately, we have to reason on. Therefore, the true logic for this world is the calculus of probabilities, which takes account of the magnitude of the probability which is or ought to be in a reasonable man's mind. So what Maxwell is saying is that probabilities are an extension of logic. That a probability is a number one assigns to a statement between 0 and 1, which expresses how much one or you or whoever does the reasoning believes in that statement being true. With 0 meaning not at all, and 1 being absolutely, and values in between expressing different degrees of uncertainty or uncertainty. This feeling by Maxwell has been formalized by Cox in 1946. So he was looking at how to extend the Boolean logic to uncertainties. And he requested three things. He requested that numbers are assigned, numbers are used in order to put, say, plausibility values to statements, and so that the degree of plausibility is represented by a real number. And it's convenient when if they are ordered, so let's assume this, but actually it is not necessary for the proof. Second, that common sense should be included. So in a limiting case, Aristotelian logic, which is about absolute truth and absolute false, must be a limiting case of this number system. And we will see in the end, the number 0 and 1 represent the probabilities or plausibilities that express truth and false. And last, the system has to be consistent. So if I give you two pieces of information in a sequence, the deductions you should draw should not depend on the order I have given you, in the order in which I've given you the two statements, unless the order has a special meaning. So if I tell you that A is true, and later on that B is true, and you do two updates, first by considering A and to be true, and then adding the information that B is true, you should come to absolutely the same conclusion, meaning the same probability value, than if I would have told you first B and then that A is true. The sequence of arguments should not change the conclusion. And from these three desideratas, Cox could show that there's an infinite number of such plausibility systems, but they are all equivalent. They are all equivalent, for example, to probability theory. So there's just a coordinate transformation between them. And probability theory is maybe the most convenient representation of them. Okay, I would say from that point on, it's clear what we have to use. We have to use probabilities in order to reason in science and elsewhere. An interesting side remark is some people have looked at what happens if instead of a single number, one assigns pairs of numbers to statements. And then it turns out that there are 5 different self-consistent systems that implement these desideratas. One is use the first number as a probability and ignore the second. And some are not so clear, but one of them actually is what we know as quantum logic. So quantum logic also seems to follow from such considerations. So let me introduce the notation for probabilities. So the probability is a number, and it depends on 2 things. It depends on the statement to which this number should be assigned, and the condition which is assumed to be correct. So we are looking at how much we believe in a statement given some condition. The condition could be some data we have, some other knowledge, whatever. But it's important that the probability always depends on these 2 elements. Yeah, and then it's a degree of belief that the statement is true, presuming that the condition is true, with truth being 1, false 0, and uncertainty numbers in between. And it's absolutely essential that we distinguish probabilities from frequencies. The frequency is how often something happens. So it is the fraction of a specific event type, for example, that it's Monday, are in a set of general events. For example, it's an arbitrary weekday, right? And we all know that frequency is 1/7. And here we have a frequency of 1, means that always a specific events happens under general, never that it's is 0. And of course, if you know a frequency and reason about the specific event, or whether it happens in a general event, then you should use this value, this frequency value, also as a probability value. So that means probabilities should be well calibrated. But there are cases where you can't do that. And let me give you examples. Let's say A is a statement, the universe is of finite size. Right? A perfect, well scientific statement. It might be true or might be wrong. And if you look at the probability of A, given what we know about the cosmos at this time, we would say the probability is larger than 0. It's possible that the universe is of finite size. We just don't know. The frequency of A is not defined. Right? Either the universe is of finite size or it's not, but is not doing different things on Mondays and Tuesdays. So in this specific case, we can have a probability, but we cannot have a frequency. Okay. You're in a lecture on statistical data analysis, and the goal of that is very often to find out what is the value of a signal. The signal might be the number you want to measure. It could be a set of number. It could be a full image. So it could be a higher dimensional mathematical object. And with these 3 arrows, I want to indicate that there is a vector space of possible signals in which you want to identify the true signal. In order to do that, you need data. So let's assume we are looking at telescope data from the satellite, and there is a data space. The data space are all possible configurations the data could take. So in the end, you will get just one data, one set of data, and from that you want to conclude what the signal is. In order to connect the data and the signal dimensions, you need a mathematical structure connecting these 2. Ideally, you would do this logic, but we learned under uncertainty we have to use probabilities. So the structure we want to use is probability theory. So what we are going to do is, first we ask how probable are the different signal configurations a priori. So for each potential signal, we have to write down a number. Well, we might just write down the function which gives us these numbers, but we somehow have to specify this function. And this function should encode all the things we know about the signal, and also characterize the uncertainty we have. Then for each of these potential signals, so this prior probability encodes our knowledge. So for each of these signal values, we write then down the conditional probability for the data given the signal. If we and that encodes our knowledge, for example, how the instrument has reacted to the signal we are measuring and how much variance there could be. If we multiply these two probabilities together, the prior probability and the likelihood, then we get the so-called joint probability of data and signal. And that gives us now the desired structure in the space of all possible data and signal configurations, helping us to navigate from the data to the signal space. Because now, well, and yeah, you remember this joint probability is just the product of these two. And now when we get the observed data, so the location in the data space is fixed, we know that the signal has to be found in the intersection of this hyperplane here in red with this probability density. And only where this probability density is high, we can expect the real signal to reside. So what we have to do is we just cut this probability cloud at the hyperspace, at this red hyperspace, and then normalize again. That's the probability gets normalized to 1. So we say the conditional probability for S now restricted to the plane given by the data is the joint probability constructed out of the product of prior and likelihood divided by the normalization constant, which is chosen such that the full thing would integrate to 1 if we integrate over S. So this is the essence of Bayes' theory. You build up the joint probability of everything that can happen about the signal you're interested in and about the data. And you build this up by multiplying a signal prior and the likelihood for the data together. You're restricted to the data that was observed, and you normalize it to 1. And the resulting probability then encodes what you have learned from the data on the signal. That is Bayes' theory. Nothing more, but also nothing less. Here it is again. So let's look at it a little bit in detail. So I've named this term. That is the so-called likelihood. That is the prior. This term down here, the normalization, is called the evidence. Why does it have this strange name? Okay, here it's mathematical definition. It should be the normalization constant. So it should ensure that if I integrate the distribution function over S, that I get 1. And this is done by just integrating the numerator and putting it to the denominator. What we should remember, is first this is given by this product. But what we should remember is that actually there's always a condition present. So in this case, the evidence is the probability of the data given M, where M stands here for all the model assumptions we did when we wrote down the prior and the likelihood. So I was sloppy in the notation before by not showing this M, but actually there's always a condition under which you have evaluated these probabilities. So, and if you look at this, you see that the evidence is actually something like a likelihood. Now, not for the signal, but for the model. It is how likely is that model would have produced that data. And we can use this model likelihood in order to make statements about the model itself. For that, you have to construct the joint probability of data, signal, and model by introducing a prior for the model, this P of M on the right, and then for each of these P of M's, the probability of the signal given the model, and then finally the likelihood of the data given the signal and the model. And with that, you can start to do model comparison and make reasoning about what is the right model. Here is how you do this. You calculate then the probability for the model given the data, which is the joint probability of data and model where the signal was marginalized, divided by an evidence which is now to be calculated for the class of models you're considering. So not only for one model. Okay. Let me also show you Bayes' theorem in a slightly different form. Here it is again. The joint probability normalized to the data you have observed. And one can rewrite this in the language of statistical mechanics as E2 minus an energy divided by a temperature, which I set to 1. So this HDS is some sort of energy which is introduced into a Boltzmann distribution. And the partition function, Z of D, is nothing than the normalization or the evidence, right? And I always can do such a construction when I define the joint probability of data and signal to be the negative logarithm of this joint probability. And actually, I like to call this quantity information or information Hamiltonian because if I know this quantity, I can make all deductions I want. The partition function is nothing than the evidence. I said this before. The normalized joint probability, whether marginalized over the signal, which was this joint probability was a product of likelihood and prior. So this transition from probabilities to this information function is nothing than a coordinate change in how we express our knowledge. Before we had probabilities, now we have negative log probabilities. And if I take this last equation, this product rule, and apply a negative logarithm to it, I get its equivalent form in information language. So the joint information of data and signal is the information of the signal, H of S, plus the information of the data given the signal. So information is additive. And that's fantastic. Because all good things in life are additive, right? Energy, momentum, all additive. Money, love, all additive. So is information. Why is this? Well, imagine you have two data sets. Well, first two things happen. First, we can look at this as a combination of a metric, something which if you look at this last expression with the eyes of machine learning, you might have seen that people write often down a metric, or in statistics. And in statistics, this is often a chi-square. Well, if your likelihood was Gaussian, then this HD of S, the HD given S, is actually a chi-square. So you have a metric which tells you how well your signal fits to the data. But then there is this second term, this regularization term, which punishes signals which are too far from what you regard as probable. Because if they're improbable, they have a low probability, so a small number, then the logarithm of the small number is very negative, and minus a negative number gives a big number. So this regularizes away solutions for the signals that are not so plausible. The other good thing about this additivity is that if you have two data sets, that you can combine the information of these two data sets. Given that they were measured independently, it is just the sum of the information of data 1 given the signal plus the information of data 2 given the signal, plus which information you had prior before getting any signal. So this formalism allows you easily to combine different data sets into joint information. Let me dwell a little bit more on this two ways of looking at things, and in order to get you a bit familiar with it. So on the left-hand side, you see a probability. Let's assume it is the probability of a one-dimensional quantity and our knowledge expressing that we have a Gaussian knowledge on what the value of S could be, right? So this blue curve is a Gaussian with some variance given by this sigma squared. If we translate this probability now to such an information Hamiltonian, we find that the information Hamiltonian is the quadratic form you have found in the E function of the Gaussian, so S squared over 2 sigma squared, plus a constant, which was a normalization constant of the prior. So that contains the same information. So any questions you can ask about probabilities, you can also ask to these information functions. So what is the maximum, for example? The maximal probability corresponds to the location of the minimum of this information function. What is the width, and so on. I'm introducing these information functions because they make certain calculations easier, and they also naturally connect to expressions you might have seen in artificial intelligence neural network trainings, where one rather works with these negative log likelihoods than with probabilities. Okay, what is important is our probability was E2 minus a quadratic form, and this information function is up to a constant, this quadratic form. And if you now get data, and let's assume our data is centered around the signal, but scatters in a Gaussian way around it. So we get a Gaussian likelihood. So this is expressed in the screen curve. If we write the corresponding information formula down, it is also a quadratic form, now S centered on D. Since information is additive, we can directly deduce that the joint information of a priori and data of signal and likelihood has to be a quadratic form as well, because a parabola plus a parabola gives a parabola, just with a mean and variance which are slightly shifted. And from that, we can immediately deduce that the posterior has to be of Gaussian shape as well. So if our prior knowledge was Gaussian, and our measurement had a Gaussian likelihood, then the posterior is also a Gaussian, with a peak somewhere in between and narrower than both of these previous Gaussians, because we have combined the knowledge encoded in both of them. The fantastic thing is this statement not only holds in one dimension, it also holds in 2, 3, and even an infinite number of dimensions. So this is a very important thing to remember. Let me look at this translation between data and signal again, just to end this. So when we get the observed data, we might want to make a statement about the signal. Is it S1 or is it S2? And so let's say, given S1 or S2, we have such distribution functions, such likelihoods. And then the question is, what should we conclude? And most people, including myself, with not given more information, would come to the frequentist conclusion that S2 looks much more plausible, because the observed data is right in the middle of the distribution function. However, I had given you the experience how important it is to fold in prior information. And the prior information might change the picture. So imagine that the prior information says, well, is such that the joint distribution looks like these contours shown here. And in this case, if you now do the Bayesian construction at looking what is the probability in the hyperplane constrained by the data, so on this red curve, you find that the peak around S1 is larger than the peak around S2, just because the probability distribution a priori was heavily towards S1. And so despite that the data points toward S2, that was not enough in order to overcome this. So a Bayesian would here come to a different conclusion than a frequentist. Okay, let me conclude. The message I want to give you with my talk is that in science, life, and love, better use Bayes. Thank you for your attention, and I hope you have some questions. I can't hear you in case you're saying something.
So if you have questions, it might be best if you come up here, or if you want to post, if you're on Zoom, then please post the questions on the chat.
Yeah. Someone needs to repeat the question because I do not see the chat window.
Yes. So the information that you have, that's different from Fisher's information, right? So for those
Yes.
of us in the room, who are more frequentists than Bayesians, and but anyway, I thought I would just first of all thank you very much. Yeah, I don't know if you want to make any comments on that, or maybe we'll wait for other questions. Yes.
Yeah, the Fisher information is basically it's a precision matrix of the data. It tells you, it encodes how sensitive the data is to your signal. And if you look at this likelihood term, which I have this HD of S, it's roughly the second derivative of it. So in this particular case, it is 1 over sigma prime squared. That will be the Fisher information. So there is a relation. If you have this information function, you can calculate the Fisher information from it.
Oh, thank you. Yeah, that's I appreciated that.
Yeah. So the word information is actually quite confusing. So what it means literally is to give shape, to form. And what is formed? Our knowledge about the world. And therefore, I think using the word information in the sense of probabilities or log probabilities is a very valid way to using it. But be aware that it's very often also used as the amount of information. So you calculate a Shannon entropy or Kullback-Leibler divergence, or the sensitivity of the Kullback-Leibler divergence to some parameters, which gives you sufficient information.
I don't see any more questions. Do you want to put your email in the chat in case there are?
I won't read emails anymore today, so.
Then I think we're good.
Then thank you, and I wish you a nice
We have
school.
one more question, actually. We do.
Yeah.
Good.
I have you briefly touched upon this. So first of all, a fantastic talk, and then bringing all those things together so that it's very super clear. But you briefly touched upon evidence, okay, evidence, and
Yeah.
which is the likelihood of the model. And as an astronomer, we sometimes have to deal with multiple models, and then for the same data, we have to use the so-called BIC, the Bayesian information criteria, to actually differentiate the likelihood of two different types of models. And there are applications of those, and there are three, at least, I think, different definitions of this criteria that I heard about. And sometimes they agree and sometimes they don't agree for given the same data. And also the evidence itself is extremely difficult to actually evaluate. So I wonder if you could, comment on that a little.
Okay, so this Bayesian information criterion is an approximation to the evidence. So it holds if you have if you can make a Gaussian approximation, then one can analytically calculate this integral which you see here, the second line, and and then the big becomes exact. However, in most situations where you are dealing with real-world complex problems, there is no closed form analytical formula. And so one does approximations, and these information criteria are different approximations to the correct thing. And therefore, they give you different answers. So the correct thing would be to calculate exactly this integral, which I have given here. If it's a one-dimensional integral, well, you go on the computer and use one of these integration schemes and you get an answer. But if S is a high-dimensional quantity, for example, an image which has 1,000,000 pixels and therefore a million-dimensional quantity, calculating a million-dimensional integral is not possible with simple integration rules. So you have to do some tricks. And there are a number of methods which try to approximate this integral. One is nested sampling, which is particularly constructed in order to calculate the evidence. And at the moment, for moderate dimensional problems, I would recommend using this and not the BAC. And yes, these things are not always trivial. And well, if it would be simple, someone else would have done it before you. So maybe you should be happy that it's not that trivial because there is still a riddle for you to be solved. Was this, did this answer your question?
Yeah, thank you for the comment. Yeah.
Yes, that did answer his question. We got one more.
Thank you for the talk. Could you go to the last second slide
Yeah.
where you,
Oh, yeah, I went to one slide too far. Let me do this here. To share again. Here we go.
yes. So I just had a conceptual question about this. Is this the same as penalizing a solution for being, just if you can find a solution, but it's only like by fine tuning? So is this the same as that? The solution that we are seeing on top right, it can be obtained by just fine tuning the parameters instead of the solution that we see in the middle, which is valid over a much larger volume. Is it similar to that? Or is this?
In this case, there are no parameters to be fine-tuned. So the point I wanted to make is do not use only the likelihood. This can be wrong. Right? That is because there is also a prior probability for S1 and S2. And this might be in a way that even if the likelihood points in one way, the prior probability still points stronger in the other way. And of course, this is an artificially constructed example just to make this particular point. A more real-life example for this point was this party situation I explained at the beginning.
Hi, I really enjoyed this. Very nice from the basics explanation. I want to make a comment before that. I want to say, like, of course, frequentist and Bayesian, this debate has gone on before I was born. It'll go on afterwards. And I do both for my astro papers. I do Bayesian for my particle physics. I do frequentist. So, but yeah, with that preface, and because there are lots of students in the audience and so on, I thought it was interesting just to mention that in a frequentist analysis, if you were to, for example, in a neutrino measurement, if there is prior information which you genuinely is a useful information, not a uninformative prior. For example, it comes from a previous measurement. In a frequentist analysis, you would incorporate it into, you would treat it like data. So you would incorporate it into the likelihood as a constraint. So it wouldn't be like totally stupid, like throwing away that information. But of course, even then, there are very good reasons to use a Bayesian method. As I think you pointed out, fine-tuning issues can be alleviated and so on. Yeah, thanks.
Well, I made this point that yes, if you have prior data, well, we had this. Okay, it came here. If you have prior data, you should include it, right? So this red line, I have two data sets, I add their log likelihoods, which is equivalent to multiplying together their likelihoods. And then it is just a question how you name things, whether you say the previous data is part of your prior or it's part of another data set. For the end result, it doesn't matter. And if you do the equivalent thing in a frequentist setting, it might be perfectly fine.
Thank you. Yes.
All right. So I think that, yeah, thanks so much, Torsten, once again. So I think on behalf of anybody in this room, thank you so much. Okay. Yes. And please post those slides or whatever PDF on Google or email it to me so that we can review them. Thanks again.
I will do so. Okay. Have a nice day. Bye.
Thank you, Torsten.
Camera is working?
Yes.
Okay.
This is your talk, correct? Yes. Awesome. This guy? No, we don't need to. I fixed it. And by that, I mean I did nothing and it worked. Oh. You're all set? The microphone is in this, so stay close to the podium.
All right. Thank you very much. My name is Michael Binger. I'm from Wiley. It's a publishing company. I think I'm one of the few non-academics here, so take it easy on me, please. There's two. Okay. So I want to talk about some fun work we did a few years ago, building Bayesian models of adaptive learning. Adaptive learning is like using computers to personalize education and give targeted recommendations to students using the data and so forth. All right, so I want to motivate this by talking about how we go from data to actionable predictive distributions. And what does our data look like? It's typically a student interaction history on a knowledge graph. So here I've shown a toy example with 4 different concepts connected by prerequisite edges, and an interaction history where the student starts on concept A, gets 2 right, 1 wrong, and then goes to concept B. These little indices tell you the order in which they did the work, which is important. And so given that, how do we get, for example, a calibrated predictive distribution on a future exam that's covering these concepts and maybe other ones that the student worked on? And also, we might be interested in recommending what the student should study next based on their history. And we might use posterior distributions on how we think they're going to respond to particular questions in the future and target them towards one where they're weaker, but they have a decent chance of success, like this middle curve here. So what are the challenges in going from this data to these predictive distributions? In particular, of course, we're going to have to build a model, a Bayesian inference model, and it needs to be very fast. It needs to handle thousands of students concurrently in real time in 100 milliseconds or less or so. And it needs to be very expressive. We need to handle the difficulty of questions and model that, and that's going to take us to our likelihood. We need to incorporate the graph structure and the interrelationships between concepts. That'll take us to our prior. And we want to account for temporal effects like recency and forgetting, and that will lead us to Gaussian processes. And then there's also the problem of calibrating the model. How do we choose the optimal hyperparameters for the prior and the Gaussian processes? So let's start. The likelihood is based on something called item response theory. It's been around for decades. It's typically used in the testing setting, like in SATs and that sort of thing. We're sort of hijacking it and using it in the adaptive setting, which is not really a testing setting because students are learning while they go. But this model is a latent student proficiency variable, which is learned from observed responses. It's going to naturally incorporate the question difficulties. And I'll just note that item here means question. So usually use the term item in this field. And the likelihood is given by the following formula, pretty simple. The probability of a correct response on item I, given the student's latent proficiency state, it's a vector of overall concepts, is just the Gaussian CDF of the proficiency on the assessed concept minus the difficulty of the item. And what does that look like? I think you know what Gaussian CDFs look like. They're S-shaped curves. But the key thing I want to point your attention to is that the difficulty shifts that curve. So a very difficult item like this purple curve means you need to have more ability to have a decent chance of answering it correctly, and vice versa for easier items. Okay, now our first problem that we're going to have to solve is recency. Recency means we want more recent things to count more than older things. Okay, and let's motivate this. Physicists like to talk about Alice and Bob. So here's Alice. She gets 5 incorrect answers in a row and then 5 correct in a row. Okay, let's compare her to Bob, who alternatingly gets incorrect and correct. Now, intuitively, because we know that there's learning going on in this environment, we think that Alice probably had an aha moment and probably gets it now. And we want to make different inferences about the knowledge states, and we want to make different interventions with the student. The problem is that IRT does not distinguish these cases, and you can see that with this curve here. This is giving the mean response probability prediction after every interaction, and you can see that Alice's curve goes down after the first 5 and it goes back up, and they both end up at 50% at the end, which is no good. That's not what we want. And this is a simple toy model, and just to get you used to seeing some of the math, this is just based on a very simple posterior for the latent proficiency theta, given the data, in terms of a standard normal prior and a product of likelihood terms that we just discussed. Okay, so this is the problem we need to solve. And we're going to do that with Gaussian processes. And the idea here is that instead of considering one latent proficiency variable for this student concept, it's actually infinitely many proficiencies at every point in time, and they evolve by a Gaussian process. And this is the same thing as taking a random variable, making a random function. And so this motivates this diagram of our model now. And we're going to start with some normal prior, the first time step, at which point there's going to be, the student's going to answer a question. The response R1 is either 0 or 1, correct or incorrect. And we're going to update our prior with the likelihood and get a posterior. And then we're going to evolve to the next time step with the Gaussian process and rinse and repeat at every time step, at every interaction. Okay, so that's a nice picture, but I haven't told you how that actually works with the math. So for that, we need the actual Gaussian process. And for this simple toy model we're building up here, we're going to move on to something more complicated later. We're using the Wiener process, which is one of the simplest Gaussian processes. It's a model used to model Brownian motion. And the properties are the following. You just have some initial condition, and your variable at some later time obeys that the mean stays the same and the variance grows linearly with time. This is a funny thing when you first see it. And this is related to the Gaussian conditional, giving the random variable at some later time in terms of some past time. And it's just a convolution where the variance is just the time increment. And we're going to use this, and we're just going to make one change. And one change is time is no longer time. Time is indexed by item interactions, questions the student answers. That's the salient feature for us. Every time a student answers a question, that's 1 unit of time. And so this leads us to the following formula. We're going to have the probability of our theta I in terms of theta I minus 1, a previous time step, is just this convolution. And we have some parameter eta, which is our recency scale. It's our recency variance scale, which is a very important parameter of the model. So let's take a look at what the math looks like now. This was the same diagram I showed you before. Now we can put math to it. And this is the math. This is the full joint posterior for all the thetas at different times in terms of the data. in terms of a normalization 1 over z, and then the prior, which is a Gaussian prior times a product of these convolutions, the Gaussian process prior terms, and then a product of likelihoods. Okay, so now let's see what this has bought us. Let's revisit Alice and Bob. So on the left is the diagram we saw before, where they both end up at 50%. And now with this model, you can see that Alice goes down again, and then after the 5 correct, we estimate roughly a 80% probability chance of success now, which is great. We have solved the problem we set out to solve. We're making what we think are better inferences about Alice's knowledge state, and we can make better recommendations and interventions with the student. However, the model I showed on the last slide, is it really tractable? And what the heck is this RNA up here? Are we doing biology now? No, we'll get to it. Okay, so let's summarize where we stand. We have this full joint posterior for the student, which we showed on the last slide. And the problem is, so we can solve this numerically in this one-dimensional case, i.e. there's a single concept. It's not too bad, but it's really too slow in the realistic case we're going to handle with multiple different concepts. We have a concept graph with hundreds of concepts. It's just not going to be tractable. So what we really need is an efficient way. We don't care so much about the joint posterior. We care about the marginal posterior that is marginalizing out all of the previous time steps, and we just want the latent knowledge state at the current time step after all the interactions have been processed. So we need to do these integrals. The problem is now you try to do these integrals, they are not tractable. You're going to get products of multiple CDS times PDS, and that's no good. So we need something else. And that something else is that RNA, which stands for the recursive normal approximation, which we're going to try to motivate here. So this is the marginal posterior that I've already showed. We're just integrating out all the previous time step variables. And I've just expanded out the products and collected terms that have theta 1 in the top line here. And there's 3 terms. There's the Gaussian PDF, a Gaussian CDF in this likelihood, and then this convolution. So I'm going to ask a question that is, what happens? What if a normal PDF times the CDF was just approximately a normal PDF? Strange question to ask, but let's just see what happens. In this red box here, we're going to say that's approximately a normal PDF. What happens then is that we're just going to convolve that with another normal PDF in terms of theta 2. And that will give us a new normal distribution. We can do that integral now. And in the bottom line here, we've done the theta 1 integral. Now we have a theta 2 integral, which I suggestively put mu1 sigma 1 squared, because in fact, this is the actual posterior after the first interaction in this framework under this approximation, if this approximation is valid. And we have the exact same setup that we had in the first line, but now with theta 2. And we can do the same thing and approximate these terms. And it recurses. So this is why it's called the recursive normal approximation all the way down. And then you can just do all the integrals. So, but there's a big if there. What about this PDF times CDF equals a PDF? Well, it's actually kind of true, weirdly. So here's the standard normal PDF, standard normal CDF, and the product normalized in the green curve. And the red dash curve is the moment matched approximation, which is pretty darn good. You can barely tell the difference. And that's what we're calling RNA here. And I'll show you, of course, it's not always good. The main thing that determines whether it's good is the prior variance of the PDF coming in. And you can see when it gets larger, the approximation starts to break down. And when it's moderate to small, when it's very small, it's almost perfect. And we're always going to be in the regime where the approximation is very good. The data prefers that, so we can actually do that. And I'll come back to that later. Okay, so now I'm ready to summarize our toy model for the single concept case. And for each item response, each student answer, we're just going to form the unnormalized posterior as the PDF prior times the CDF likelihood. And we're going to compute moments, 3 moments. The 0th moment, which is the normalization, the first moment, which is going to give us our new mean, and the second moment, which is going to give us our variance. And then, because of the lovely properties of convolving a Gaussian with the Gaussian process effects, just add. And you just add to the variance, the recency scale. And then you just say that this mean and variance we calculated, which will end up being exact integrals that you can do, but the thing that is not exact is saying that they are for a normal PDF. That is where the approximation comes in. And that becomes the prior for the next step. You can just do it all. Okay, so none of this would be useful at all if it didn't work for the multi-concept case. So I've set up the basic program. Let's see if we can extend it to the general case. So for example, consider a 3-chain here, 3 different concepts, A, B, C, linked by prerequisite edges, like so. And this motivates this diagram of our model now, where we start with a multivariate normal prior. And we have some observation at time 1, and we encode that with the IRT likelihood. And then we evolve all of the concepts together with the Gaussian process to step 2, where the same thing happens in some repeat. So the key questions are, can we now do the moment matching integrals and maintain this nice recursive closed form iterative approximation? 2, how does the prior, this multivariate normal prior, relate to the graph structure? We'd like to actually have that. And 3, what is our Gaussian process now? Okay, so first question, can we do the integrals? So here's a multivariate normal prior. Hopefully you've seen it before. We're just going to start with the most general form for now. And we're going to have the same likelihood we had before, the normal CDF. And so what we're going to want is the RNA posterior. We're going to exclude recency right now. We'll come back to it because it's just additive. It's easy if this works. After a single response R, here is our unnormalized posterior. Here's our normalization term. And we're going to approximate that as a multivariate normal. That's the RNA approximation, where the 3 moment integrals are. The 0th moment is the normalization. The first moment is the mean vector now. And the second moment is going to give us the covariance matrix. So that's what we have to do. And of course, I wouldn't be here if we can't do those integrals. And I'll show you the results, which are maybe not so useful to show up, but I will anyway. So the integrals can be done via Cholesky decomposition. They're very tedious to do, but this is what they look like. And I'll point out a couple of key things you should take away. First, this normalization is actually the marginal likelihood of a response. And we'll come back to that when we're talking about calibrating the model. 2, so these are the core update equations for the mean vector and covariance matrix. And just to be clear, this is giving the knowledge state after a response R in terms of the knowledge state before the interaction. So this is the before mu's and sigmas, and this is the after mu's. And in terms of the item parameters, i.e. the item difficulties, these betas. Okay. And the algorithm is order number of concepts squared due to this outer product. And this is an outer product of the CEF covariance column vector of the covariance matrix, where C is the concept that you answered, that you interacted with. Okay. So there we go. Let's move on to the graph structured prior. So I've just used the most general multivariate normal prior thus far. So we're going to want the dependencies to be governed by our knowledge graph. So we have actually domain experts to build these knowledge graphs with the prerequisite edges, and we want to code that so that proficiencies flow between related concepts. So how are we going to do that? So there's actually a theorem you can find in some textbooks that any multivariate normal distribution can be written in terms of a Gaussian Bayes net and vice versa. And so in pictures and equations, that kind of looks like this. Here we might have a knowledge graph with four concepts. And you can write that as a, if you consider that a Gaussian Bayes net, you can write that as a multivariate Gaussian in terms of the 4 proficiencies on these concepts. And the independencies of the Gaussian Bayes net, like V structures and direct edges, are encoded in non-zero elements of the precision matrix, the inverse of the covariance matrix. And this is also a formula you can find in a textbook that relates the weight matrix of your knowledge graph, where the weights are the prerequisite edges connecting concepts, to the precision matrix, the inverse covariance matrix of your multivariate normal. And we're introducing just one prior variance scale. You can introduce multiple if you want, but keeping it simple here. Okay, and finally, their third key question in the multivariate case, what is our recency Gaussian process? Let's start with, I'm going to not do this justice, so I'm just going to present the results. If you start with the most general conditional for your theta vectors at I and I minus 1, in terms of some arbitrary symmetric covariance matrix, it turns out, you just have to trust me on this, there's some consistency conditions that you can use to constrain the form of K. And it's avoiding spurious proficiency accumulation. I can explain what that means afterwards if you want, but it's rather tedious. But basically, and it turns out that K then becomes a outer product of covariance vectors, exactly the same form we saw before in the update equations, which is nice. And what this means actually is, it's kind of nice, the effects of the item interactions purely by themselves and recency must flow through the graph and mutate the graph in the same way. Otherwise, you get kind of spurious things. It's kind of neat. Okay, so now I've set the framework for the model. And so what are some fun things you can do with the model? I'm going to just go over one of the fun things you can do. There's many ways that it can be extended I won't have time to get into, but here's one of them. Student learning. Okay, so in our framework, in our product that we built, students learn by interacting with the material. They get answer explanations, instruction, and they study offline, okay? And we accommodate this by this learning with recency, as we've discussed before. However, we do not predict our model learning, and let me explain what that means. So here's the plot for some real data, and the green curve is the average percent correct for students that on their first 4 questions they did in the product, let's just say, were all on the same concept. And you can see that the percent correct goes from 63, 64% up to almost 80%. And the blue curve is when the first 4 questions were all on different concepts. So you can see it's flat there. And so what this means is they're learning by doing, regardless, this is whether they get it right or wrong. Okay. However, IRT and RNA, as we've developed it thus far, if you go through it, you can quickly convince yourself it predicts an exactly flat learning curve here. So we don't predict learning. So this is the problem we want to solve. And how we're going to do that is we're going to extend the model to learn other content parameters in addition to the student proficiencies. So we're going to have a latent vector X now, which is actually going to contain all the students' proficiencies, all the difficulties for different questions and also the concepts, and per concept learning rates, which are indexed by the student interaction number on a concept. So if it's the second time they interact on that concept, then it would be 2. And we're going to have a new likelihood now. It's still based on the same Gaussian CDF, but more terms in it, more latent parameters. And so sync here student item number on that concept, and this weight vector pulls out the right elements of this big vector, which contains, like I said, for all the students, all the items, everything, and just these particular ones. And you can, and that's our learning rate parameter, by the way. And this yields a model that you can be solved in exactly the same way we showed before. The update equations look very similar. You could almost guess them. They involve this weight vector. And so I won't go into that, but let's look at some of the results from running that model. And this is across 8 different domains, which are 8 different knowledge graphs, each of which has hundreds of concepts. And what I'm showing here on the y-axis is the question number on the LO. So if yours is the 5th question you've answered on this, sorry, LO is concept. 5th question you've answered on this concept, that you'd be here, the data point there. And the gray curves are each concept. And the blue curves are averaging in a principled way over all of the concepts in the domain. And you can see that we've now kind of explained that green curve we saw before. We're predicting learning by doing. So that's cool. Okay, now I've got only a few minutes left. I want to touch a little bit on calibrating the model. And I'm going to try to talk about 3 different methods we use. One of them is on item by item data. We use the log marginal likelihood, and then 2 different metrics for trying to calibrate our model on exam scores. Okay, log marginal likelihood. Let's justify that. And luckily, the previous talk was great and kind of motivated a lot of this. Here's base formula condition. Now I've added M as in the model choice, which includes the architecture and the hyperparameters. And this normalization here is the marginal likelihood and we've computed that already, we've seen. And it's useful because it allows us to compare models. You want to compare the probability of model 1 with model 2. You can actually write that in terms of these marginal likelihood ratios, assuming that your prior for the two models are the same, which is valid if they're the same dimensionality. And we get this marginal likelihood for free when we compute RNA. You have to compute it because you're computing the normalization. So all we have to do is take a logarithm and sum to get all the marginal likelihoods. And this allows us to tune our hyperparameters. And what that might look like in practice is you look for, this is for one domain. You have a heat map here of y-axis is the prior variance scale, which is a key hyperparameter, and the y-axis is the recency scale. With funny acronyms, so don't worry about that. The data seems to prefer this dark green area, which is a prior variance around 0.7 and some non-zero recency. And this kind of justifies that we're always in the regime where the RNA approximation is very good. So that's neat. Another thing you can do is look at posteriors for exams. So this is some toy data actually, but so this is the posterior prediction for exam score, and this is the observed score. How are we doing here? Well, it's, looks okay. I don't know, but we would want to put numbers to this. And for that, you would develop a scoring rule, which basically is a function of your posterior distribution and the observed score, and it gives you a penalty. And this would allow you to tell you, will tell you how well you're doing on predicting the exam scores. And what makes the scoring rule good? I'm going to probably not discuss this because I think I'm running out of time. Well, there's a notion of proper scoring rules. There's some deep math involved. I think it's neat. I don't entirely understand it all, but it's basically a principled way to evaluate probabilistic predictions. I've shown some examples here. The bold ones are proper scoring rules. The gray ones are not. For different types of inference, like binary and continuous target variables and different types of model outputs. And I'll just point out that in our case, we use something called the continuous rank probability score. This is defined as an integral of the CDF and a Heaviside function. Don't worry about it now. Don't have time to get into it. It's kind of confusing, but it's actually a generalization of the Breyer score to the continuous case. And so we use this to calibrate our model. And in my last 1 minute, I am going to try to get through this last slide. Basically, we show in our product confidence intervals of the form. You have a 50% chance to score between, say, a 75 and 90. And well, how do you calibrate that? Well, you could look at all the times you said that, and hopefully 50% of the time it was true, right? But making that more principled, basically, you could take each observation, pass it through your model CDF for that student, and look at all the resulting values. And it should be a uniform distribution by the probability integral transform theorem, which is a thing I learned just a few days ago that it has a name, but it's pretty intuitive and you can show it yourself. And so that's what we're going to do. And one thing you can do is just by looking at histograms. So this is the CDF values of our model on the observed exam scores. And you can see it's pretty flat. A perfectly calibrated model would be exactly flat. This is not quite as good as the discretization effects, but if you want to not just look at histograms and put a number to it, one thing you can do is take the KL divergence of the histograms with the true uniform distribution, and that would allow you to say that, in fact, this model and its hyperparameters is better than this model and its hyperparameters. And that's all I got. There's a lot of other fun things you can do. You can model forgetting with a different Gaussian process called the Ornstein-Uhlenbeck process, and you can model lots of other things. But that's all I got. Over time. Thank you very much.
I think we might reserve questions for the coffee break, if that's all right. We have one more talk in this morning session by Jack Wagner. So Jack, oh, please.
Just the drive.
You're just on the drive, all
Yeah.
right. Want to help me find it?
Yeah. Wagner, you can probably search probably at the bottom if this is alphabetically sorted. Yeah, right at the bottom.
This guy.
Yes.
It's easier probably just to open it here, right?
Yeah. It's all good. I did it in Google Slides, so it should be more convenient.
down is next, and the microphone is the laptop.
Thank you. Alrighty, good morning. Thank you all for being here. Hope not to keep you too long from your coffee break. My name is Jack Wagner. I'm a graduate student here at UAH, working with Dr. Sukanya Chakrabarty, mostly working in terms of galactic dynamics and trying to constrain dark matter profiles. But today I'll be talking to you guys about Markov chain Monte Carlo regression for the analysis of stellar radial velocities. Now, radial velocities will probably sound similar to you. Whoops. Because that was kind of part of the focus of the Cocktails and Cosmos talk Friday night, if any of you had the luck to attend. It's very popular among the exoplanet community for determining if a star has a companion. As you can see from the hypnotizing animation here, as a star and a companion or any number of companions orbit about a center of mass, there's a wobble induced in the star. And the movement of the star away from and towards an observer causes Doppler shifts. And these Doppler shifts can be measured across a reference spectral baseline, as evidenced by the left and right motion here. And we mark that with changes in measured radial velocities. Now, my work does not look for exoplanets. I'm very against exoplanets. They are a distraction for me. I'm looking for single stars because what I want to do is actually work on galactic-induced accelerations. So I want to say if you have a single star by itself, no companions, any changes to those radial velocities should be caused by the acceleration induced by the Milky Way. Why do I care? Recent studies have shown the Milky Way is not symmetric. There are a lot of asymmetries that are not precisely understood necessarily, that still need better constraints. And as such, it may or may not be possible to constrain that from direct measurements of accelerations. And so in the lower right here, Chakrabarty et al. 2020, we have this simulated expectation of how different celestial bodies will be affected by galactic acceleration. As you can see, binaries are this large green line, and they get all out of whack. They're very intense radial velocity changes, and as such, contaminant. Likewise, exoplanets are smaller in their changes, but also contaminants. So we're looking at just these single stars in blue, and this is a change of about 10 centimeters per second across a decade. And that's very, very small. In fact, about 3 times 10 to the negative 8 centimeters per second squared. This is very precise. And but thankfully, we're entering eras of spectrograph precision that are very, very precise. High res is the work I'll be talking about most of this talk that has an instrumental precision about 1 meter per second. But espresso and moving forward have instrumental precisions closer to 10 centimeters per second, and as such, might be better suited for this sort of constraint. Now, what are the difficulties with determining these accelerations? If I set a star by itself, then any radial velocity changes are caused by acceleration induced by the galaxy, then linear regression, velocity over time, acceleration. Boom. Unfortunately, this is not the case. Stars are not billiard balls shooting across the pool table of the Milky Way. They have a variety of factors that we call stellar jitter that make this constraint somewhat difficult. Magnetic activity, sunspot activity here, causes various changes in measured flux lines that make it appear like the star is moving when it might not actually be moving. In addition, granulation caused by the convective nature of a star, and even changes to the structure of the star itself, because these are not perfect spheres, they jiggle a bit, cause difficulties with this. So how do I fix that? Well, if we take this to a base case and we pretend like we're not modeling a star and any of its actual attributes, we just look at it from a pure velocity over time estimation. This is HG12051. There's a wonderful survey by Lee Rosenthal called the California Legacy Survey that collects 719 F, G, K, and M type stars in the search for exoplanets. So I feel like a bit of a mooch stealing all this exoplanet data for my purposes, but we'll work with it. They found about 10 additional stars in addition to confirming about 167 exoplanets. So from that, I'm able to look at 500 stars where there were no detections of exoplanets and say, let's go from here. This star is known as an RV standard because in addition to having a multitude of measurements, the spread of the radial velocities is within 10 meters per second. And so looking at it, if I do a plain y equals mx plus b linear regression, I get a value of accelerations about -3 times 10 to the -7 centimeters per second squared with an error of about half that value. It's not great. It doesn't really match the averages presented on the previous slide either. But also, if I do a linear correlation coefficient, it's very bad. The fit is very close to 0, practically 10 to the negative 14. And as such, there have to be ways to actually model stellar activity, and thankfully, there are. Gaussian process modeling has become very popular among exoplanet community recently, both in the purpose of analyzing light curves as well as radial velocities. Dye et al. In 2017 have presented this excellent graphic here, where based off of a star, they're able to successfully detrend not only the exoplanet signal, but also the Gaussian process signal in blue based off of the stellar activity. As the exoplanet signal is mostly periodic, you see that yellow kind of, it almost looks like noise buzz here, and red, they combine it to successfully replicate the radial velocity trends. I am using Radvel for the purpose of this work. It's a Keplerian orbit solving software that features several Gaussian process kernels with which to model the stellar activity. Of course, it's designed for implementation with exoplanets, but thankfully, there are ways to work with it that do not involve injecting exoplanets into the stellar sample, so I use it for my purposes. Radvel methodology. So initial parameters. Often exoplanet hunters will use stuff like a test light curve to kind of provide estimates as to stellar rotation periods or other parameters. I'm kind of throwing darts at a dartboard here, providing rather vague initial priors with the purpose of iterating a process and then kind of solving a bit later. After providing initial parameters, do a maximum a posteriori fit, and as we repeat this process, shift from sort of hard uniform priors into more specialized distributions to hopefully narrow down to a successful value. And of course, after getting these maximum a posteriori fits, Radvel performed a Markov chain Monte Carlo method to try and hone in on that stellar activity. So taking a look back at this star with Gaussian processes, specifically with a Celerite kernel developed by Foreman Mackey 2017, this is a bit of a simplified model for computational efficiency in which we use B, C, and L hyperparameters that don't have any real physical meaning with which to get this Gaussian kernel. The only physical trait of the kernel is the period of rotation, which hopefully we can constrain because the rotation period of a star is somewhat fundamental to its stellar activity. So far, not the best showing. In my work with Radvel, I'm mostly getting these sort of flat end results on both rotation period as well as the C hyperparameter. So a lot of my work recently has been trying to debug this. Still working on it. Now, for example, this fit of the star returns an acceleration of about 5.6 × 10⁻11 centimeters per second squared, with an error of larger than that. So again, not a very well-constrained acceleration, and I'm still working to determine if that's, again, due to work on the Radvel itself, trying to develop better models, whether that's a result of instrumental precision. There are also various catalog updates to the California Legacy Survey. Butler et al., which published a whole bunch of high-res radial velocity data, has had an update in 2019 by Lev Talor, where they're like, we found these systematic errors, we're going to account for this. And then 2 months ago, Jerusalem Teklu is like, hey, we found more systematic errors, let's update those. And so if you recall back to Dr. Lyon's talk on Friday morning, the virtual review, you can argue that I'm bad systematics because I'm not using systematics that I've worked with personally, working from another sample. And so you actually look at the base curve here. You have this large kind of background, whether that's jitter from the instrument or whether that's the expected stellar rotation signal, still working to understand. There's also the nature where I'm working on a much larger time scale than prior work. I mean, this is a survey that's taken place over a decade, whether as you compare to the prior work, this was about 60 days of observations. So I am a bit curious if I might be looking at too broad of a time scale to actually resolve the stellar activity. So that's also something that I'm working on. And with that actually mostly brings me to the end of my talk. I'm not trying to keep you guys from coffee for too long. So in summary, analyses of these radial velocities can help understand the galactic potential, providing information on the nature and distribution of dark matter, which is, of course, always a hot topic issue. These acceleration measurements are hampered by stellar activity or jitter, in addition to instrumental precision. Thankfully, instrumental precision is getting better with every decade. and we have a better understanding of stellar activity every passing year. And through the use of RADVAL, I'm attempting to model this jitter with known statistical methods and extract accelerations, still very much a work in progress. So I appreciate the opportunity to talk here and learn so much about statistics from so many of you. This has been a very informative workshop, and I thank you. Well, I guess I can point, yeah. Thank you.
Wondering black holes, black holes in the Milky Way are like cold gas halos or like molecular clouds, globular clusters, all that stuff.
That's an excellent question. And to my knowledge, no, not yet. Again, these are looking at very somewhat small scale systems. Exoplanet hunters are mostly looking to extract very consistent periodic signals from something. And that's on a much smaller baseline. And so larger effects, that would likely, it's something to think about, because I don't think it would be necessary. It would not be a good idea to ignore that idea when you're trying to say, oh, this is how the dark matter is distributed, if you're not accounting for those sorts of environmental factors. But currently in this kinematic basis, not really.
So you mentioned you're working with high-res data. There's comparable UVIS on VLT, right? It has pretty similar resolution. So have you looked into that? I think it also has a catalog. I don't have the exact details, but I think it also has a stellar catalog, a pretty large one.
I've not looked into that one yet. Again, I've mostly been following the California Legacy Survey, which uses high-res, Lick Hamilton, and the APF Levy Planet Finder spectrograph. It's a compilation of that data. Of course, there's almost too many spectrographs to look for in this case. And for the purposes of this talk, I was mostly showing data from exclusively the post-upgrade high-res stuff. So I'm not accounting for multi-instrument systematic errors quite yet, although RADVAL does proclaim the proficiency to account for multiple instrument composite likelihood fits. Sure.
Some posterior distributions from your MCMC that look flattish and
yes,
don't like them or something like that. And I was wondering, I mean, uniform distribution is, still be a good one. I was wondering what was your thinking there and why you don't.
Well, I mean, I would prefer to have a more concrete kind of response on this rotation period, because without, if the errors on the rotation period are large, I mean, this is a value of about 25 days plus or minus 13 days. If it's not resolving a rotation period narrowly, I'm concerned about the nature of how it's determining the quasi-periodic oscillations from that stellar activity, especially with how stellar activity is well tied to rotation periods. So if I think that it's not constraining that rotation period very well, then I'm not confident on the actual complete radial velocity fit.
Let's follow up on the question. So are you putting the data to test cycles or what exactly?
No, I'm doing this on a purely radial velocity basis. So these are all radial velocity measurements. There has been some discussion about whether or not you can properly recover the rotation period from radial velocities alone, or if you can only recover about a third of that properly. With more, I mean, I'd be happy to do more collaborations with people who are more familiar with photometry and test light curves to kind of provide better estimates for this. But I am attempting to conclude this exclusively from radial velocities, partially because in conjunction with this work, we're doing espresso time series observations with a more precise spectrograph where we exclusively have these radial velocity measurements. And so being able to determine this exclusively from radial velocity would help motivate that work as well.
The reason I ask is, I mean, if you have stars, you're going to get different back. And if the contamination on the star, you're not going to get any.
No, and part of the motivation for certain stars is to mitigate magnetic activity, sunspots and the like. We mostly focus on subgiant stars that are moving off of the main branch, so they have somewhat diluted stellar activity. He 1251 is a G9 type subgiant. Of course, magnetic activity is something, and these differential rotations are something that are difficult to account for, even in a quasi-periodic setting. But I mean, it's a model. We're trying our best.
Just one quick question. At this kind of regime of radial velocity, we're dominated actually by the Earth's rotation itself.
Yes.
And the jitter of the Earth, as well as its orbit around the sun, right? So I wonder how well you will actually, when people actually calibrate out those systematics in their process of removing a signal, let's say that is on a period of 365 days, and then for 24 hours. How much of that process of removing the systematics could have already removed the signal that you are looking for?
Well, that's a good question. I can't speak with too much familiarity on the removal of systematics based off of the work done by the people who operate these spectrographs. But I would be surprised if the detrending of the Earth-based systematics was causing too much removal in the radial velocity space. But I'm not sure. That's an interesting question. I'd have to look into it.
Because it's in terms of signal.
Yeah.
We're talking about 30 kilometers per second.
Yeah. But I mean, again, I trust that the people who use these spectrographs are relatively confident in their methods of removing the Earth-based systematics. Otherwise, I would question why they publish all this data.
Coffee break until 11 o'clock, and we'll meet back.
Right, yeah, so. We see a lot of them going to the accurate and very good. Finding out what is like,
Okay, so I guess we got the honors here, and I guess Eric, I mean, I don't really need to say much except, take it away with the statistics problem for gamma ray bursts.
Okay. So I thank the organizers for the invite. I'm going to very briefly introduce gamma ray bursts. It's not the point of my talk, but they're the most luminous events in the universe, and we want to study them because they involve physics extremes that we can't reproduce on Earth. We've used these for the first precise measurement of the speed of gravity. We know where gold comes from because of these events. We use them to study dense matter, the extremes of QCD, and also sometimes the extremes of quantum electrodynamics as well. We have complicated statistical problems. Sometimes you want to associate gamma ray bursts to another signal, say a gravitational wave or an optical detection. You need this enabled to make these strong claims. But because of how complex these systems are, we don't really understand them. So how can you associate things? How can you have robust statistical significance assignment when you can't properly and fully describe your system or even your detectors? So gamma ray bursts, most of them come from the ends of massive stars. They're rotating very quickly. As the core collapses, it forms a black hole. The rotation gives you accretion, which drive jets. These propagate out at the speed of light. And if they're oriented towards Earth, you will detect them as a short burst of gamma rays. This was an animation done for an event we saw last year. We've been detecting these for 60 years. What we detect are count rates over time. These are like glorified Geiger counters. This is background subtracted, so your background is basically 0, and you see these flashes and pulses that arise. So this is going to step through some gamma ray bursts that Fermi GBM has seen. Fermi GBM is headquartered here in Huntsville. Each of these is about 10 times brighter than the last. Each of these is a kind of a huge advancement in our field in understanding one way or another. This was the previous brightest burst we'd seen until a couple years ago when we had this detection. In terms of understanding your detectors and your instrument, you can see at the top here, it's kind of cut off. That's because the count rate was so high, our detectors couldn't keep up with readout. So Stephen did an enormous amount of work basically emulating the electronics on the spacecraft to correct out that saturation. And this was the actual brightness we infer. So in 60 years of observing, this little red one is the second brightest one we've seen. So we call this one the brightest of all time. We learned a great deal about gamma ray bursts because it turns out if you can see something with way more counts than before, it makes it easier to learn to do complicated studies. There was also an unexpected result. So I want to talk about line significance. This is a very generic problem. Do you have a line? Can you claim 3 or 5 sigma detections? This comes up in particle physics, in nuclear physics, looking for new particles or resonances. It comes up in astrophysics quite often. And in my field, in gamma ray bursts, this was an enormously controversial topic. In the 90s, there was an argument of are gamma ray bursts cosmological or galactic? The answer now is we know they're cosmological, but the proof that they were galactic is people were claiming the detections of lines. The reasons for this are quite subtle. Our response matrices are not invertible. What that means is on the right, you see as a function of energy, and that's differential flux. You're inferring a flux distribution, but what you infer in the flux distribution is model dependent. This is 2 joined power laws on top. If you have a single power law or something else, those data points will shift. It's a forward folding process. There's no way around this. So you can't just use, for example, the amplitude of a line to get a measurement. So this is real data from the boat. On the top is assuming a smoothly broken power law. You have this break here, and they claim that there's a line, an MEV line. Every single person in the field believes this is not true because this was the #1 debate in the field for more than a decade. When this came out, I didn't believe this was real either. Do any of you have a guess on how we can properly quantify significance for a line detection? Not you. That would be great. The people in my field, they typically use what's called Bayesian inference criterion, or I actually don't know how to say it, Akake inference criterion. In this case, it's something like a chi-square difference, but you're using likelihood statistics, so it's modified. And the argument is, does the change in your fit statistic justify the additional parameters? In this particular case, you cannot use this approach. This is what the release paper used, and it was an incorrect statistical approach. The reason for this is what's called a regularity condition. You, in some sense, do Wilks and Wald apply? In this case, the regularity condition is called identifiability, meaning can you always tell the difference between option B, we'll say option 1 and option 2? In this case, if your amplitude is 0, these are identical and you cannot differentiate them. So that criterion is violated. So we use false alarm rates. Strictly speaking, this is not a false alarm rate. We're not doing it as a function of time, but it is a calculation of how often by chance can you get a signal as significant as what you see. And Gabby introduced this last night. The approach itself is very easy to describe, but setting it up is exceptionally difficult. That is largely the work that Gabby described yesterday, is LIGO spending more than a decade figuring out how to do this properly. In our case, this is our procedure. We're going to fit your continuum only model. You're going to fit your continuum plus your Gaussian line, and you're going to compare your fit statistic. In this case, it's p-stat. What we're interested in is the delta p-stat. How much does it change between these two? Now you need to generate a background. You need to see how often is this occurring by chance. You assume your continuum model is true. You inject that into your data. For that, you fit both of those models and you measure a delta p-stat. And you do this millions of times. And you generate a background distribution. And then you say, how often does your background distribution out of the total number of events simulated exceed your real value? So this is what we see. On the right, on the far right in green, this is the measured value in reality. The way you read significance is the distance from here horizontally to your background distribution in blue, and you can see very clearly that this vastly exceeds phi sigma. So Stephen and I did this work. I was quite surprised. This is the first time that I've had a very strong opinion in the field, which was that this line wasn't real, and I was objectively wrong, which is always an interesting thing. So it is definitely a real detection. This has taught us something new about gamma ray burst. Additionally, you can see the effect of the regularity condition violation. This is basically your distribution if Wilks and Wald was always valid, and you can see this deviation here. This is the most significant interval. I picked that to make a clean story, but there are other intervals where this violation does matter. So that's one type of gamma ray burst. This is a second one. Gabby mentioned neutron star mergers last night. This was an animation done for 170817. They're losing energy to gravitational waves shown in blue. That causes them to in-spiral until they merge and explode. Again, you'll power ultra-relativistic jets, which release gamma rays, and a bunch of other things happen, that being the origin of gold. So we waited for this for a long time. LIGO was built to detect neutron star mergers. Fermi was built to detect short gamma ray bursts before we knew that these came from the same source. This is what happened in real time. So we, similarly to the story of 150914, both teams built hugely complicated searches to deal with weak signals. And it turns out this, at the time, this, for a long time, this was the second loudest gravitational wave detection. And that was an onboard trigger on Fermi. So I did my dissertation here on subthreshold searches. How do you identify short gamma ray bursts if you don't see them on board? Turns out that didn't matter. But more generally, you can work out that we should see far more joint detections that are weak than loud. Interferometers scale instead of inverse distance squared. The amplitude is just inverse distance. If you take their SNR 8 cut, you imagine instead something in SNR 4. If you have two SNR 4 detections in gravitational waves, say a 10 sigma detection in gamma rays 2 seconds later, that is a clear and objective joint detection. But you're going from 8 to 4 on gravitational waves means you've doubled your detection distance, which means your volume is increased by a factor of 8. So we should see something on the order of 5 to 10 more detections that are sub-threshold or weaker than we do these very loud ones. So can we robustly identify them? Again, we're going to build a false alarm rate. Step one is always set your ranking statistic. On the right, this is what we're using in a modern sense. We're combining data from both sides together into a single coherent false alarm rate. This is a little complicated. The numerator, you have what is a temporal overlap. So basically, are these things close in time? We expect them to be very close, within typically a few seconds. And this is a spatial overlap calculation. How well do the posterior localizations on the sky agree with each other? The denominator is, in some sense, a penalty factor. These are probabilities or odds ratios that a given signal is real. The lower the chance that a signal is real, you're going to get a larger denominator, so you're going to decrease your ranking statistic. This doesn't have to be perfect. It just has to properly capture your expectations. This is where we're at now after a decade. You measure this in real data, and then you somehow have to come up with a way to emulate background. We can't repeat the experiment. You have to do things like time slides or work them out that way. My number one caution for all of you is you ever do something like this, and more generally, is be aware of the look elsewhere effect. I would argue this is the single greatest problem in my field, that people neglect this, which is if we have a gravitational wave, in this case centered at 0 seconds, we can run all of our searches and we're going to identify a nice signal. I forgot to update the time scale here. Imagine you have up here a 4-second signal. It's a very clear 4-second signal. It's a large likelihood ratio. It's a clear, real detection. When you're generating your background, you cannot only look for 4-second events. You have to look for anything that you would consider a viable short gamma ray burst, which could be anywhere from fractions of a second to even 8 seconds in duration. If you don't account for anything you would consider valid, you're going to give way too strong a statement on your statistical validity. In the past year alone, there have been multiple major press releases from leading institutions that have totally screwed this calculation up. And it causes people spend years working on things that are not real joint associations. So this, I think, is one of two takeaways I would like you to take. So in our case, how do we avoid this? We're using that full parameter space of what we consider valid. We have these sky maps. If we want to generate background, we can slide time. We have our real data that's aligned. We can just offset, say, the gamma ray data by a minute. We don't expect those things to be related. That's a way for us to kind of emulate a background distribution. The other key piece, in the numerator, we had spatial overlap. In this case, these two things are coming from the same part in the sky. You have your whole sample of gravitational wave localizations, all of your gamma ray burst ones. You have pairs like this that are real, but you can just shift between them and randomly sample and generate out your background distribution. This is not released, but this is the result of the current search for the third observing run. Using this whole process, they now use what's called the inverse FAR. So how often does this occur? In this case, once every few years. You can see a little mild excess, but this is not statistically significant. We've had weekly meetings for more than a decade. We have real expectations. We should have 10 times as many threshold events as real ones, but we have not found anything yet. So sometimes you can spend a lot of effort and it doesn't pay off for a long time. Okay. My third example of gamma ray bursts, these ones in our detectors appear quite similar, but they have a very different physical origin. In this case, you have a neutron star, very strong magnetic field. Like we have earthquakes on Earth, these have starquakes. If you amplify that with a magnetic field, you can get what are called magnetar giant flares, huge outbursts of energy. The strongest signals to hit Earth that are not from the sun are these events in the Milky Way. They look like this. You have a short spike in a periodic tail. But if they're outside of the Milky Way, the tail is no longer detectable, and this looks just like a short gamma ray burst. We've known about this for 30 years. We've expected that some of the short gamma ray bursts we see, instead of arising from cosmological neutron star mergers, are actually arising from magnetars in nearby galaxies, in this case, the Sculptor galaxy. We can identify these by spatial alignment. We know every nearby galaxy. We've cataloged all of them. If we have a real event from them, they will be localized to that region. Again, we're doing this with a false alarm rate. We call this one omega. It's a measurement of the agreement of two spatial distributions. If you take your sphere, the sky, you discretize it, you get pixels of size A, you get your gamma ray burst localization. It looks like that red box at the end. This last one is the complicated piece. If the event is a magnetite giant flare, where do you expect it to fall in the sky? We know it should come from nearby galaxies. The insight I had is it should also track the star formation rate. We think magnetars come from core collapse supernovae. Those don't last very long. Magnetars don't last very long. So the magnetar formation rate should track this linearly. This is the more complicated thing. This is how bright they are. How far out can we detect them? More energetic ones you can detect further into the universe, but they're less common. They have a much lower rate. So you fold all of this into a single ranking statistic. You then measure it from your real data. You then simulate your background and you measure your statistic. So one insight is kind of taking in the information and the expectations we already have from these events. The other one is then how do you simulate the background? We're using data from a dozen satellites over 40 years. Calculating things like exposure functions in any reliable manner is effectively impossible. So in this case, instead of rotating our real data, instead of rotating our detections, we rotate galaxy catalogs. So we're rotating the universe to generate our background distribution. You can do this on individual events. This was an event from 4 years ago, which itself is something like a 4 sigma detection. Or you can do it on the population level. Here's our ranking statistic, the cumulative fraction out of 250. You can run simulations on the population level to get your confidence intervals. And you see at 2, 3, and 4 events, we exceed 5 sigma detection significance. Okay, generally I avoid talking about or focusing on my own work, especially in invited talks. In this case, I've not done that because one of the unique things I have in the field is that I can construct false alarm rates pretty reliably. This has led to me having more than 10 papers where I did this calculation myself, came up with these approaches. There's derived papers that have come from this. One of my students who's here, ultimately his PhD thesis came up because I decided to study magnetars because an event went off and I could quantify it. As one more, so if you can learn statistics, if you can learn novel techniques, you can make careers on that. This extragalactic magnetar flare claim, people argued about it in my field for 30 years. I proved that at 5 sigma discovery significance, finally we can just accept it and move on. That measurement could have been done 18 years ago. The data has been sitting there the whole time. We already had the 3 events we needed, but people just didn't combine things in the appropriate manner. So novel statistical techniques, I think, are quite important. And I did my PhD here. I wish a conference like this had happened at the time. So I'm very glad to be here and for you all to be here. So these are my last comments. I think in most statistical approaches, the cleverness is in the approach itself. In false alarm rates, I think it's backwards. Once you've constructed things properly, it is a trivial calculation. The only thing you have to worry about is have you run enough of a background that you get out of low count regime for constraining your events. It's just a Poisson counting problem. That's the only thing you have to worry about. In what I've shown and in what Gabby talked about last night, the problem is in constructing your ranking statistic appropriately and in making sure that when you're doing background simulations, you're not neglecting something. And those 2 things are generally pretty difficult to do. And one more time, do not fall for look elsewhere effect. So thank you, and I'm happy to take any questions.
You basically offering anything which is related to another galaxy as a magnetar flare. So are all GRBs and just list or?
Yeah, okay, so the question is, if things that we say are aligned with nearby galaxies, we're calling giant flares. And then our other gamma ray bursts hostless. This is a fantastic question. When in this sample, we ended up claiming that there's 4 events that we were saying are nearby extragalactic giant flares. The statistical quantification to hit 5 sigma was done only on spatial alignment and assuming it tracked star formation. Strictly speaking, that could give you things like gamma ray bursts from massive stars, which do occur. So the second step of the paper was looking at the properties of these giant flares. So you can see this one is, the main spike is only, say, 10 milliseconds long. All 4 of them are super short. That matches expectations from giant flares. Other gamma ray bursts are several seconds, hundreds of seconds long. And we did additional checks like, is there a supernova? Were there gravitational waves for neutron star mergers? So we did this additional sanity check. Most gamma ray burst localizations are hostless. The median redshift for long gamma ray bursts is 2, which is, I don't know, 11 billion years ago. This will change with Rubin. Rubin's so powerful that we begin to map out galaxy catalogs to a redshift of 0.5. We should then be able to automatically identify nearby events, which we're very excited about. And hopefully we can do that starting next year.
And so, I'm not sure false alarm is the right term, because false alarm, as far as I know, also includes, it's a combination of false positives and false negatives. Whereas to me, it seems like what you're constructing is a null distribution, or recalibrating your null distribution, and getting a better sense of the type 1 now. So,
Yeah, I agree. I was talking to Gabby about this, which is that these techniques they developed in multiple different fields. They have become standard approaches in multiple fields, including in time domain and multi-messenger. There is not like a single paper that describes these things. So there's subtle, like several other things I talked about are not false alarm rates. So I have not been careful in my language in some sense because we haven't agreed on the language to use.
Yeah, but I will make the comment that, I really, this is very interesting that what you said is that you had to go that route of building this null distribution or whatever you want to call it, precisely because actually in your case, the delta chi-square effectively, you couldn't use it because of parameter identifiability, which is actually a very subtle point that, is interesting that you brought it up. To tell you the truth, this is the first time that I see it in such a clear context. So I thought I would just mention it. So yeah, that was, just a comment.
Yeah, well, I'll add that Stephen and I pulled this up, but it was relying on the arguments from the 90s, which was the BATC team in Huntsville that worked through all these subtleties in our field for the first time.
Yeah, yes, I didn't hear that long, so yes. Going directly, being an extra astronomer, still talking to the gamma ray people, that's fine. Yeah. Anyway, yeah, one more question.
Really enjoyed your talk and this discussion over the Picasso effect. Really great. I have maybe a naive question. So for the Picasso effect, at least the way we were doing it in physics, you would really need to decide exactly how you're going to look at the data before, and then you never look at new views of the data, right? So
Yeah.
Surely you can't actually do that.
Yeah, okay. So the question was in look elsewhere effect. I wrote this here. Oh no, I deleted it. Okay. I had a comment that I deleted. The comment was, ideally you predefine your search criterion. So in this work, in this work, we predefined the time offsets that are allowable using the best theory we had at the time. We predefined the time scales that we consider to be viable for short gamma ray bursts. So here, everything is well constructed ahead of time. You do not violate it if there's any way that you can just make the measurement cleanly. And I totally agree with that. The problem with my field is we don't understand things particularly well. So let's say there's, if you have a nearby long gamma ray burst that's rotating very quickly, you might expect to get a gravitational wave signal out to say tens of megaparsecs. You may, it's at the nearest maybe 50 galaxies. If you then say, I would expect, this is a supernova, you would expect to get an X-ray shock breakout signal. People don't know when that occurs. We have no idea how long that delay time is. How long does the explosion take to propagate through the star? So how do you predefine your construction? So this is the real root of the problems in my field. People find things. Oh, I found this flare that's a month long that could be associated to this thing. and then they don't go any further. They don't say, oh, I would have considered this if it was a week or 3 months. And that is the root of the problem. So on the one hand, people aren't careful. On the other hand, our field is discovery driven. And so this is a very difficult problem to solve if you don't know what you're looking for ahead of time. I'm envious of particle physics in that regard.
We could, yeah, could we go to slide 8, please? The one with the engine. Yes, so what is the physical reason for this?
Oh, yeah, I had the same question. So-
Yeah.
Can I read them?
Yeah.
Okay, so I didn't show this, but they found this in multiple timescales. So this is 300 to 320. At 280 seconds, they see this at 15 MeV. Here it's about, I think, 10 MeV, and over about a minute, it slides down into 4 MeV. And so that was initially part of why we didn't believe it, because lines are stationary, especially nuclear lines. The interpretation, okay. We have inhomogeneous accretion. So you have your traditional legend, you're getting accretion. The way we believe this occurs, you're sending out multiple shocks into the jet. When the shocks collide, you get your gamma ray burst emission. The idea here is, in this case, is the first one that went out slowed down. It had a gamma of about 20. The huge bulk emission hits this, causing positron-electron annihilation. That shell is slowing down because it's getting hit by surrounding material. It's getting hit by additional things, re-energizing antimatter annihilation. So the argument is that this is a positron annihilation line. I tend to favor that, but I think it's not. I think there are still other explanations that people are exploring.
Then the shift is just the jet slowing down because it.
Yeah.
Yeah.
Yeah, right.
Okay, wonderful. Yes, so let's thank Eric once again. Okay, and so we are continuing on with the.
Yeah,
James
down is
to talk
next,
to us
and
about-
the microphone is in here, so stay close.
Gentlemen?
Thank you. Thanks, everyone. I'm really happy to be here. So I'm going to be talking about generative models and scientific inference. So let's get some context. Intractable likelihoods. These are ubiquitous in science. From the smallest scales of, objects in particle collisions, for example, to massive scales, of course, in cosmology. And many of these complex phenomena can only be meaningfully represented with a forward model. So likelihood-free inference is in demand. So this is to say that having inference when you can't evaluate the likelihood function, but instead can only evaluate the forward simulator, and having methods for these contexts is challenging. So maybe to motivate the reason for this language, likelihood-free. In the first case, I think of some unavailable likelihoods as being intractable. For example, some of the likelihoods in high-energy physics, they depend on integrals without closed form solutions. In Earth system modeling, sometimes you'll be coupling differential equations on different time scales. This is a very hard thing to compute quickly. And then we also have cases where maybe you have an explicit likelihood, but it takes some time to evaluate it, and to deploy it on massive catalogs of objects on the order of billions of objects is just impossible. Okay. Now, machine learning addresses some of these challenges for likelihood-free inference. When you are using neural models, they can scale without bespoke dimension reduction, and they can accelerate computation by orders of magnitude. So leveraging machine learning is highly desirable. And in fact, machine learning has been leveraged for these kinds of problems to equip the scientist for traditional statistical inference, either via the likelihood or via the posterior. Both have been explored in this context. Now, generative models have been used for the posterior-based approach. If you have some training set, just a collection of pairs of labels theta and measurements x, you can train a generative model, call it pi, and it will be an approximator to the posterior. Here, just a selection of some recent works across various domains that use this approach for likelihood-free inference. Now, generative models are suited for prediction. When I'm talking about generative models, I'm mostly talking specifically about neural density estimators. These are, for example, normalizing flows, diffusion models, flow matching, and they combine what is effectively a prior, which would be the empirical marginal of the labels in the training data. You can think sort of analogously in LLMs, there's a prior over language, which is the distribution of language that occurs on the internet, for example. And then a forward model, a simulator, or it could simply be samples observed under the data generating process that nature is. So generative models, they excel at producing complex data, but how can we use them to recover the hidden parameters from observed data? Okay. And the point is, neural density estimators, they often critically fail for inference. So even if the neural density estimator was a perfect estimator of the posterior distribution, the true posterior distribution corresponding to the true likelihood and the prior that you want to operate on, the posterior-based approach can fail in inverse problems in two key ways. So the first key way, which I'll explain shortly, is the lack of validity for individual instances or experimental units. And the second is the results can be biased on average as a consequence when the train and target data don't match. So let's talk about the lack of validity for individual cases. So in this picture, I am showing, it might be faint. I hope you can see the outline of a prior. It's a Gaussian prior in one dimension. And it's a prior that I've prescribed for inference on some unknown parameter whose true value I've denoted theta star A. Now, I'll train a generative model, and from it, I can suppose, hypothetically, I'm simulating a collection of samples under the likelihood at theta star A, and now I'm just inspecting the coverage rate of the credible intervals that I get from this posterior. And when the true parameter is not close to the mode of the training prior, I have very poor coverage. Maybe I was hoping that I'd cover 80% of the time, but I'm not getting close. In the second row, the true parameter is theta star B. It's closer to the mode of the prior. And we can see that our coverage is closer to what we expect. So this is a known property of posteriors. It's a challenging property to work around because we don't necessarily have information about rare events with respect to our training data, say. So it's a known issue about posteriors. As a consequence, suppose your train and target distributions differ. Although for individual instances close to the mode of the prior, you might have desired coverage, because most of the target objects might be far from that mode, you'll miscover on average. So that's another undesirable failure mode. Okay, with the remaining time, I'm going to talk about the method that we supply to address these issues. So this is a preprint from earlier in the summer with my advisor, Ann Lee, and also Josh Ingram, who's here in the audience today, along with a number of other colleagues. Okay, so we introduced the frequentist Bayes confidence procedure. This procedure provides guarantees for individuals. It's not just providing coverage on average with respect to a population. And it's also precise when the train and target data happen to match. Importantly, this works in a sample size n equals 1 setting, and it's completely amortized, which is to say that once you train your estimators in the procedure, you don't need to train them again. You can deploy them over and over again for a number of different populations. The assumption for the experimental setting is that we have 3 splits of data. The first being for training the posterior, and then 2 more splits, one for calibration, one for target data. And we're going to require, crucially, that the calibration data has the same likelihood as the target data. That is coming from the true data generating process. In principle, and this is a technicality, you don't actually require the training data to come from the true distribution. Okay, the framework is modular. It starts with training an estimator for the posterior. I won't talk about this. I'll assume that we have the posterior ready. Then there's a second step, which is reshaping the posterior into what are called p-values. So this actually tracks sort of the last talk that Dr. Burns gave, where I think it's a fairly close analogy between the false alarm rate, which is a p-value in my mind for a detection problem. Here, I'm writing down a p-value function for the whole parameter space of theta. Here I want to just get the null distribution of, in this case, a test statistic, my posterior, as a function of theta. So I'm going to estimate this function of theta. And then with this function, I'll simply report as my confidence set the set of values of the parameter for which the p-value does not fall below the significance level. That's 1 minus the confidence level. So if I want confidence level 90%, I'll write down significance level 10.1, and I'm just going to retain the values of the parameter for which the p-value does not fall below that significance level. Okay, so that's a p-value function. And then lastly, and technically this is an optional branch of the framework, is estimating local diagnostics. So this is just a way of actually checking that you have the coverage that you desire with the p-value function. So here is a follow-up on that synthetic 1D example that I showed earlier. In the top left is the posterior and one of the credible intervals. Okay, thank you. And one of the credible intervals is shown just below. In the top right, I'm showing the local coverage probability. So we see here that the coverage probability is close to the nominal level of 90% near the center of the parameter space where the prior is highest, but it falls off very quickly. In the second row, I have the p-value function. It looks similar to the p-value, similar to the posterior, excuse me. It's a little bit wider. And in fact, when you check coverage, it does have nominal coverage approximately. Okay, so with the remaining few minutes, I'm going to talk about one case study in astrophysics. So here we're resolving conflicting results from differing models of nature. So here's a setup. Suppose we have 2 different models for the population of stars in the Milky Way. One population called Model D is disk biased. That's just to say that we'll maybe say that the true population of stars we believe is mostly disk. And then maybe a differing scientist thinks that we're underestimating the representation of stars in the Milky Way that occur in the halo. So these 2 different models imply 2 different populations of stars. Here, you could parameterize it with an age metallicity curve. And these models also imply different priors, naturally, on the stellar labels within that population. So here I just have some pair plots of contours of the priors that are induced by those two models. Here, the labels I'm looking at are log G, effective temperature, surface metallicity, right? We have two different priors. And those two different priors give two different posteriors. So here are some level sets from those posteriors and the resulting credible sets that we get for 90% high posterior density. These posteriors disagree. So here for an example point, theta, marked as a red star, we see the disk biased posterior fails to cover the true parameter. In fact, both posteriors fail to cover in the full dimensionality of the parameter space, but you can't see that in the 2D projections. So I do have in the legend, estimated coverage is 0%. With the freebie procedure, we get confidence sets that cover close to the nominal level. Here we see 90%, 92%, pretty close to what we desire. And in this figure, which is a bit hard to parse, but let me try. We have above the diagonal, the pair plots, the full 5-dimensional parameter space that we've estimated the posterior, the local coverage. So it's a function of theta, the labels, the probability that the high posterior density region actually recovers a true parameter. In this case, the color is showing that coverage rate. Red is bad, green is good. And below the diagonal is the coverage for our procedure freebie. This is all for the halo biased model. This is the result for the disk biased model. Okay, so the freebie framework, it leverages posterior based estimators, but it doesn't sacrifice local frequentist coverage. And in our paper, we apply freebie to two, I think, realistic astrophysics examples, including one, which is an example of likelihood-free inference beyond simulator-based inference. I have some supplementary slides on that if you'd like to talk about that. Here's a link to the preprint. We have code that's publicly available, and I'd be more than happy to take any questions either here or remotely.
Take a question here, and then of course we have lunch upcoming shortly, and maybe more during the break. But anybody with any questions for things here? Yes, please.
I'll ask a question. So
Sure.
You mentioned you need these to perform the procedure. You need 3 splits of data, right? You train diagnostic grants, and then you have this calibration set, right? Could you explain, like, maybe a scientific setting, like what this calibration set might represent, maybe like an observational study?
Sure. I think that's a good segue, in fact, to our likelihood-free without simulator example. So maybe we could flip forward just to look at a picture of case study 2, in which we do exactly what Josh has asked about. So here's a picture from the paper. We're looking at 2 different settings. These are both the keel diagrams for the Milky Way, where on the left, we're showing the full sort of uniform distribution over the keel diagram. And on the right, just a subset in which there's some selection bias that's occurred. These are both implemented in practice from collections of labels that have been cross-matched between, I think it was Gaia and SPSS data sets. So the case in point here is that the prior could simply be the distribution of the labels that you have in the catalog that you have available, but then some subset might have to be extracted for the calibration step, in which case that could be, yeah, sampled to be some uniform collection. Yeah. Yeah, I hope I did some justice to your question.
Okay, in that case, thanks so much.
Thank you.
A quick second here. Yeah. Here's the Zoom. Down is next, and the microphone is this laptop.
We have Soham, who is going to continue on the Bayesian methods for calibration of spacecraft instruments.
Hi. Hello, everyone. Today I'll be talking about application of a Bayesian hierarchical model in calibration of space-based instrument. This project is with my advisor Yang and Harman, Vinay is here, and David. Okay, so let's start with the problem setup. With X-ray detector, we try to detect the number of photons coming from a photon source. So the photon that is coming from an astronomical source that has a particular distribution or a spectrum. Let's denote it by Q. That depends on the energy E and parameter theta. Theta depends on the source S. Now, how do we estimate this? Estimate the number of photons? We just simply integrate the density, the photon density, over a given passband range. Let's consider the yellow patch as the range of as a passband or energy range. We integrate the density over that range, and that's how we get the photon flux for source S and the passband P. Right now, we use space-based instrument like X-ray detector to measure these photons. Over time, for old instruments, over time it might have some measurement shift. Also, new instrument that are just launched, that might also have some instrument-specific shift. And just using one instrument, we cannot detect those instrument-specific shift from the value of FSP. So what we have to do, we have to collect multiple instruments and measure such photons from same set of multiple sources and analyze the overall data set to see if there is any source specific or instrument specific shift. Okay, so for now, we know the value of the parameters that are used to calculate this photon count. What we would do, we would use these parameters in our spectral formula to calculate the photon counts, and then for each observation, for each instrument and source, and then use this aggregated data, put it in a Bayesian hierarchical model to estimate these parameters back and compare that with the previous value we have used to evaluate the photon counts. Right now, if they do not match, such disagreement would mean that that particular instrument is not agreeing with the overall data set. All right, so how do we do it? We take a reasonable range of energy from the middle portion of the energy range, because we are trying to create a standardized calibration procedure. So we are working with the good data, meaning the energy is from the high density area, so that the photon count is maximum as possible. And we are also working with bright stars. So we split our range, or the working range of energy, that is 0.15 to 10 kilo electron volt, into 10 small intervals called passbands. And for each of these passband, I am calculating the total photon count C for instrument I, source S, passband interval P, and kth channel within the passband P. And that's we use this formula integrated over the passband EP to get the total photon count for that particular passband under channel K. So for now, we know all the terms, T, A, alpha, all these things. Capital A is going to be our parameter, and we would estimate this capital A back and compare with this current value that we are using to calculate the photon count. So capital A is actually the coefficient of effective area. We would call it simply effective area. That depends on instrument and the passband. And if we could rewrite that, so AIP doesn't depend on E, so that goes out of the integral, and we can rewrite this as product of T, A, and F. A is the effective area, F is flux. Note that F depends on the source and passband, which is correct because consecutive passband should be, the consecutive passband photon flux should be it should depend on the passband, and the effective area is instrument specific factor. It depends on only instrument and passband. Right now we aggregate over K channels within passband P to get the aggregated value, aggregated photon count for instrument I, source S, and passband P. Right? Okay. Now we are using multiple instrument and source to get this photon count data C. This is our final observed value, final data set that we'll be working on. So we have total 10 instrument, 10 passbands, and 46 sources. Total 4600 combination available. And this is the 3D data array that we'll be working on. We have one replication of such data array. The color is proportionate to the log of the photon count C. Color is proportional to the log of C. I will explain why I'm using log. The white cells correspond to missing values. There are a lot of missing values, almost 50%, and we had to disregard some of the observation because of many reasons. One is look at the second slit. So that is for the second source, the values are quite large compared to other values. So for that source, the photon count is so high, the star is bright, so it is kind of messing up with the all other observations. So we had to delete that source and all observation corresponding that source. So finally, we use this photon count to model. We are going to the statistical part. Model it as CISP equals to product of T and effective area A and flux F with the noise, that is the log normal noise. Again, we are taking at the log scale because if we take log of this expression, then we get very good additive form. And the left hand side is known because T is estimated without the parameter we are talking about, and C is our observed value. So we could write the left hand side as Y. Y is our final response variable. And on the right hand side, we have this additive form where B is the log effective area, capital G is the log flux, and epsilon is the noise, a log of the previous log normal noise, which epsilon follows Gaussian distribution with mean 0 and variance sigma square. Note that variance sigma square, that is the model variance, that is also additive in the equation with B and G, which means when we apply prior distribution on the parameters, at the posterior level, the posterior mean and variance will be interconnected through this parameter sigma. Because this sigma is additive, this sigma's control is affecting the location, and also through the variance of epsilon, it affects the variance of the parameters. So this form is not is not the usual linear regression. So we cannot have a good closed form solution for the posterior of the parameters B, G, and sigma. Hence, we use Monte Carlo technique to simulate the values of the parameters and then estimate from the posterior values. Right? We use Hamiltonian Monte Carlo with no U-turn sampler to simulate the values. For reference, I have the equation on the top right corner. Now, based on the particular prior structure we apply on the model parameters, which are B, G, and sigma, we have three different models. So for this equation, we have roughly 2000 observation and 500 parameters. So it is kind of over parameterized, and the parameters could be uh, could be non-identifiable at the posterior level. So that is why we need to apply the priors in hierarchical setup so that we can um, connect all the parameters so that even in weakly identifiable setup, the parameters could be estimated properly. And that is the advantage of hierarchical Bayesian model, which this method can give, which other frequentist or Bayesian method cannot. Okay. For example, if I look into, okay, I'll talk about that later. So in model 1 and 2, for log effective area B, I am applying the Gaussian prior with 0 mean. B is bold letter B. That is a vectorized format of B. And in between model 1 and 2, in model 1, we do not have any correlation, any prior correlation. So the prior covariance matrix gamma I of B, that in model 1, that is diagonal matrix. In model 2, it has a correlation. It is not diagonal. So we want to see how is the effect of correlation within the passbands between between the passbands within one instrument of effective area. And for log flux, we have non-informative prior. That means flat prior for the G. And for error sigma, we have inverse gamma prior with uncertainty parameter nu. The variance parameter tau square are given by the astronomers, and the error hyperparameter nu I is also given by astronomers. So for model 3, we have same prior for log effective area, but for log flux, we have little complicated prior. For only for model 3, we have the hierarchical prior setup. So G, the vector G, has Gaussian prior with mean small g, and small g has this formula where look at the log value, because we are talking about log flux. That's why we have the log of the integral, and we use the power law to calculate the log flux. Here we have scale parameter A and two hyperparameters BC. So this A, BC are hyperparameters. Now how this is hierarchical prior, because we have the main equation B plus G, and on G we have the Gaussian prior, and the mean is expressed by this equation where it contains further hyperparameters ABC, and ABC has some prior, some uniform or non-informative prior. So that is the hierarchy we are talking about. One disadvantage with hierarchical prior is that hyperparameters such as ABC, which are high up in the hierarchy, those are harder to estimate. So we need to keep that in mind. And we are trying to compare between these three models to see which one is the most, which one is a better fit, adjusted to the number of parameters involved in the model, and also which one has the most expressive prior structure. For example, of course, if model 3 is somewhat comparable to model 2 and 1, we prefer model 3. Okay. Now the issues we have to look for is, first one is the non-informative prior on log flux. For model 1 and 2, since we are using flat prior for log flux, we need to see if at the posterior level, if the posterior distributions are proper or not. And since the B and G are additive, these two parameter B and G might not be identifiable at the posterior level. So we have two propositions through which we have theoretically proved that the properness and parameter identifiability of the posterior for model 1 and 2 are possible. And the specification of the prior variance for log effective area, that is another issue. So if I have, this is a heat map, grayscale heat map of the prior variance. On the rows, I have the 10 instrument, and on the column, I have 10 passband ranges. For each instrument and passband, I have the prior variance. This is actually standard deviation, prior standard deviation. The NA values are where we do not have standard deviation given. We do not have any prior values. So we had to discard all the observation corresponding those indices. Note that towards the end passbands, we have high standard deviation, high error rate. And that would be a problematic when we have small sample size, since we are estimating parameters. Effective number of sample for each parameter is actually small. Overall, we have 2000, but for each parameter, the effective number of observation is small. So this prior specification is actually important. If the sample size is low for certain parameters, then it might change the posterior estimates. Okay. And then the third thing I want to mention is that the hyperparameters ABC are scalar, and we are also trying to make it even complicated, where A would depend on source S and B and C would depend on target T. So what is source and target? So source is not a typical photon source. It's actually target observed at different GTI. So these are considered as different sources, and we could make these hyperparameters A, B, C dependent on such source and target to have more complex model. Yep. Thank you. Any questions?
Time for a quick question.
Yeah.
Thank you so much. Yeah. Maybe I do have a quick question then. Why was the error term log normal? Is that because of the product of variables, or maybe that's
Log
not-
normal has the multiplicative form.
Right.
Yes.
And then in log form.
And then take log to have this typical Gaussian. That's the idea.
Right.
Yeah.
Okay, I'll always continue the discussion over lunch, and we'll see you all at the 2 o'clock here now. Okay, thank you so much.
For everyone online, we're off to lunch and it starts again in roughly 2 hours. And I'll leave the schedule with an arrow up on the Zoom in case anyone, comes in and looks at it. You'll see where we're at.